All right, so good evening, everyone. Welcome to today's Math Online Tutorial class. My name is Felix Agnesh, your tutor as usual, and this is going to be week 4's class. And we're going to be looking at polynomials, logarithms, and inequalities. So, if you remember, when we had last week's class, we looked at quadratic equations and related topics surrounding it. So now we're going a step further, and we're going to be looking at polynomials, which are higher order level. Okay, so quadratic equations. So we'll get right into it when we see the first one, but then just give you an idea of how this relates to what we did in the previous week. And so we're going to be building on the knowledge you already had for sure. So at the end of today's or this week's class, things that you're expected to master or have in mind are a mastery of polynomials, understanding polynomials, and being able to perform operations of them. So like I said before, last week we looked at quadratic equations. Now quadratic equations are equations that are up to degree 2, right? But then we also have equations that are dealt 3 and high. So those are known as polynomial. Of course, poly means many, right? So when we hear polyhedron or polyand, we're talking about more than a lot. So we're going to be looking at polynomials up to degree 3. We're going to be applying theorems that are involved, which are the factor and related theorems that solve polynomial problems. We're also going to be looking at logarithms, so we're going to be simplifying and evaluating logarithm expressions using change of base. And then we're going to look at inequalities, so sublinear, quadratic, and absolute value inequalities, effectively. So at the end of this lesson, these are the things that you're expected to have achieved, and hopefully you will do so by the time we get to the end. So without further ado, let's get right into it. All right, so polynomials, first of all, we're going to talk about polynomials. Like I said before in introduction, we are looking at equations where the highest power is 3 or more. So that's what we mean when we talk about polynomials, right? So when we look at quadratic equation, remember we're dealing with the case where we have the highest power to 2. Now, when the highest power is 1, we know that's the linear equation. We are used to that's the equation. What we know for algebra, right? Linear algebra. So we're just dealing with the straight line equation. But then we now progress for that to 2, where we have quadratic equation, and we look at how to solve those methods and formulas that are involved in that. Now we go a step further, and of course, when solving actually real life problems, you'll see that equations arise where you have up to 3 or 3 or even 4 or 5 as the case may be. So these ones are given as polynomials. And of course, general expression a plus a1x plus a2x plus a and x and n less than or equals to b. Right. So this is general form of polynomial equation, and then our n is 3 in this case. Now we have some examples here. Where for this polynomial, it's a linear polynomial, it's a quadratic, it's a cubic. Now this is linear because our variable x here has the highest degree of it to be 1, right? So we know x, of course, we can't see the 1, but then we know that x is power 1 is x. So this is the linear equation. And of course, if you have to plot this, you get a straight line graph, hence the name linear. Now we say this is quadratic because if you look at the variable, you see that the highest power variable is 2. So this is an equation of degree 2 in that sense, and so it's the quadratic equation. Now for this one, we are seeing that the highest variable is degree 3, so we have a cubic equation. And of course, this goes for us. We have I don't think we have particular names for all of them going up to infinity. But we have particular names for this one, this polynomial, so linear, quadratic, and cubic. And of course, if you go further, you have equation degree 4, 5, 6, 7, as the case may be. So it's important to recognize what you're working with. Of course, you need to identify what kind of equation it is. You have to know the best possible means of solving it, right? So of course, operations that can perform on polynomial include addition, subtraction, multiplication, and division, right? So next slide is going to be looking at the factor and remainder theorems. Now, when working with polynomials, there are 2 theorems that are kind of closely related, so we're going to be looking at them together, and that's the factor theorem and the remainder theorem. Now, what is the factor theorem? The factor theorem is that if f of a is equal to 0, then x minus a is a factor of x. Now, that looks like a lot of ground, right? So we're going to break that down. But then let's look at the remainder theorem quite closely because, like I said, they're all related. The remainder theorem says the remainder of f of x divided by x minus a is f of a. Of course, that looks like much gibberish, but then it's going to become clear very soon when we look at the example. So first of all, the factor theorem, what does this actually mean? If f of a is 0, then x minus a is the factor of f of x, right? So first of all, f of x is our equation, is our function, is whatever the polynomial we are given to work with this. So for example, what we have here, f of x is x cubed minus 3x squared plus 2x. Now the factor theorem says that if f of a is equal to 0, now what does it mean? What does f of a actually mean? So it means that you have a constant a, right? And of course you have the original equation f of x, right? Now you have a constant a, and you are asked to find f of a. So what that simply means is that in your equation, you're going to replace anywhere that x appears with your constant a. And since a is a constant, you're going to evaluate it and you're going to give you a constant value of answer, right? So for example, if a was 2, right, and you had your f of x here, which is the case here, you would substitute x for 2 in every single place and then evaluate what f of x will give you, and that would be your f of a. Now, what does the factor theorem now state? Having established what f of x is and what f of a is. Now, the factor theorem states that if f of a is 0, right, so if you substitute a into this equation and your final answer is 0, then subsequently x minus a is a factor of f of x, is a factor of your polynomial or your linear or whatever equation it is you have. So this is a theorem that I'm proving. So I mean, the example here shows check if x minus 2 is a factor of this, right? So the factor theorem says that if f of a is 0, then x minus a is a factor of x, factor of x. And now so they're giving us x minus 2 and asking us to check if it is a factor of this, right? Now, when we want to now find this out, we apply the factor theorem. And so we have that a comparing this with this. So we have x minus 2, we have x minus 2. What does this tell us? That our a is 2, right? So what we now do is f of 2. Now, if f of 2 gives us 0, then we know that x minus 2 is a factor of this equation. If f of 2 does not give us 0, then we know that x minus 2 is not a factor of f of x, right? So now what we do? We take our 2 and put it in every single place where x appears. So we have x cubed minus 3x squared plus 2x. Now our a in this case is now 2. So what we do is 2 cubed minus 3x minus 3 into bracket 2 squared plus 2 times 2. And if you have to evaluate that, so this is going to give you 8 8 minus 3 times 4 is 12, 8 minus 12 minus 4 plus 4. So minus 4 plus 4 is giving you 0. So we see clearly that f of 2 is 0. And then what conclusion do we draw from that? Conclusion is that x minus 2 is actually a factor of this equation f of x. And so that's what it means. That's how the factor theorem actually works. And the factor theorem is actually an easier way of doing this because, of course, so let's go to numbers, right? If I give you two numbers, because if I said check if 2 is a factor of 20, what will you do? If 2 is a factor of 20, prove to me that it's a factor of 20, what will you do? You do 20 divided by 2, and show me that 20 divided by 2 gives you an answer without the remainder, right? And so there's no remainder, it means that 2 is a factor of 20. Now, if I do check if is a factor of 20, what would you do? You do 20 divided by 3, and you show me that you get 6 remainder 2, meaning that 3 is not a factor of 20. Now, the same thing applies even when you're working with polynomials, right? So ideally, what we would have done would be, do f of x, so x minus 3x plus 2x divided by x minus 2. And it is actually possible to do that, right? You divide that. It's just like a normal long division where x minus 3x plus 2x is on the inside and x minus 2 is outside, and you divide it. And you do that, and you would see that your remainder would be 0, right? And so that would prove to you that x minus 2 is the factor of this. However, of course, the factor theorem provides an easier way, provides a shortcut in a sense, where you can simply just substitute a when you are given x minus a and put it into your f of x and know whether it's the factor or not, right? So having the factor theorem also makes it easier because knowing this, showing you that f minus 2 is the factor, it also means that 2 is the root of this equation, right? That's if it's the polynomial equation that was created to solve. It shows you that 2 is the root of this equation, right? So there are many other angles that can come out of this, but basically this is how the factor theorem works, and this is going to be used going further to solving many other things as well.
Did you stop talking on? I can't hear anything.
I think probably it's a glitch or network stuff, but let's just hold on a bit.
All right, so sorry, I had to take a short break. So picking up when we stopped, the next is the remainder theorem. Now, the remainder theorem says that the remainder of f of x divided by x minus a is f of a. Interesting. So what does that mean? Now, there's an example here to illustrate that for us. Now, if you take x squared plus 3x plus 2 and divide it by x minus 1, right? The remainder theorem is now giving us an easier way out as well. So instead of doing this long division, right, to now find what the remainder is going to be, the remainder theorem simply says if you have x minus a, right, and now in this example, our x minus a is x minus 1, right? So it tells us that if you substitute a into your equation, whatever you get is the remainder of this division, right? So if we were to apply that here, what we'll now do would be to do f of 1, right? And that would mean to substitute 1 into this equation, and that would be 1 squared plus 3 times 1 plus 2, which is 1 plus 3 plus 2, which is 6. And now this tells us two things, right? So it tells us that, of course, by virtue of the remainder theorem, it tells us that if you were to do this divided by this, your remainder will be 6, right? And now it also tells us that x minus 1 is not the factor of x squared plus 3x plus 2. Why is that the case? Because we have a remainder, because we have a non-zero remainder. We have a remainder basically, it's not 0. So it means that x minus 1 is not the factor of our given equation f of x. And that also means that x minus 1 is not a root of this equation. And I hope you remember what roots are right from our quadratic equations. It means that if this equation f of x was created to 0, x minus 1 is not a root of the equation. So this is another helpful tool in that be able to identify when you have a factor, a polynomial, or when you have a root of quadratic equation, whatever it is. So by virtue of the remainder theorem, you can simply, without going to the process of a long quotient or doing a long division, find the remainder of our given equation. So now next slide, we have some more examples here which are going to address the point. So on factor theorem, we are given x squared minus x cubed minus 2x minus x plus 2, and we are asked to test x minus 1. Now we know that if we have x minus a, we should do f of a. So now we have x minus 1, so our a is going to be 1. Now if we substitute 1 into this equation, we're going to have 1 cubed minus 2 into bracket 1 squared minus 1 plus 2, and that's going to be 1 minus 2 minus 1 plus 2. And if you resolve all of that out, it's 1 cancels 1, minus 2 cancels plus 2, and now we're left with 0. So we can say with certainty that x minus 1 is a factor of our equation, our given equation of f of x, right? Now, another example, we are given this divided by x plus 2. Now, what the remainder and factor theorem have told us is that if you have x minus a, you should do f of a, right? But now we have something slightly different here, because this is why it's a example to look at. So you have x plus 2, right? But then the theorem that we are working with says if you have x minus a, then we're going to test f of a, right? But now we have x plus 2. So our a is not 2 in this case, now our a is minus 2, right? So you think about it, if you have x minus a, if you want to represent x plus 2 in that x minus a format, you have x minus 2, right? Because minus minus is plus. So our a now, when we have x plus 2, is not 2, but actually minus 2. Because the general form for the factor theorem and the remainder theorem is actually x minus a. So I hope that's clear why this now is minus 2. So what we are going to do now here is f of minus 2. So we substitute in minus 2 into f of x, and then we see that we have a remainder of minus 15. So by the definition of the remainder theorem, it means that if you were to divide this by this, f of x by our given quotient x plus 2, our given dividend, our answer minus 15 is the remainder of that division. So those are more examples on how, where, and when the factor theorem or the remainder theorem is applied, right? So next slide we're going to be looking at is solving higher degree polynomials, right? Solving higher degree polynomials. Now, previously we looked at quadratic equations, right? We looked at quadratic equations, and we outlined 3 methods of quadratic equations. If you remember very clearly, so we looked at the factorization method, we looked at the completing the square method, and we looked at the quadratic formula plus geometry. So we looked at 3 different ways of being able to combat for being able to combat product equation and find the roots of the equation. Now, for higher degree polynomials, in this case, we're looking at the cubic polynomial. Now, this is cubic because our x, our variable, has the highest power, n equals 3. So we say this is a cubic polynomial. Now, most of the methods that we looked at we will not apply in so many cubic polynomials, factorization of square and the Almighty formula. So now we have to devise new means of being able to combat or solve higher degree polynomials. And so for this particular example, where we have a cubic polynomial, we do something called a root test or a root check, right? So when we had a quadratic polynomial, we had two possible answers. Now, when we have a cubic polynomial, we're going to have 3 possible answers. So as the degree of the polynomial increases, the number of possible answers, the number of roots of the equation also increases, right? So for a cubic polynomial, we're going to have 3 roots. They might be the same, they might be distinct, also might be similar, distinct, but we're going to have 3 roots, right? So what does that mean? 3 different points where the curve passes through the x-axis. That's what the equation is. Now, for a fourth order polynomial, we're going to have 4 roots. For a fifth order polynomial, we're going to have 5 roots, and so on and so forth. So having that in mind is pretty important because it enables you to know where to start solutions and so on. Now, from the factor theorem, if you remember, I talked about the fact that to know that one thing you can do from factor theorem is that when you put in your f of a or whatever it is and it gives you 0, you can be assured that x minus a is a root of that equation. Now, this is where pretty much the first step in being able to tackle a cubic polynomial. So you, by trial and error, first of all, determine or find one of the roots, right? You find one of the roots. So, and how do you do that? So you just plug in numbers into the equation and then see if it gives you 0, right? Now, from our factor theorem, we know that if you put in any number into this equation and it gives you 0, it means that x minus that number is one of the roots of the equation, right? And so it's best to always start with lower possible numbers or numbers that are very small and then work your way up from there because the roots are normally around there. So for example, if I was to pick 1, okay, let's have 0. So if I try 0, right? If I put 0 into this equation, this is going to be 0 cubed minus 2 times 0 squared minus 0 plus 2. So all of this is going to become 0 and I'm left with plus 2. And then my answer to this equation is 2. Now, that is obvious that 0 is not the root of the equation because by virtue of the factor theorem, I should get the 0 as my answer as when I plug in f of 0 to prove to me that 0 is a factor. So that's not the case. So we can try negative numbers, we can try positive numbers, but of course, like I said, it's best always start low and then because I mean it's going to be a lot of trial and error, right? So if I say let me put 1 now in this equation, what do I have? 1 cubed minus 2 times 1 squared minus 1 plus 2, and that goes to 1 minus 1, that comes out to be 0 minus 2 plus 2, that comes out to be 0, right? So we see now that if you put 1 into this equation, you're going to get 0 as your answer. What does that mean? It means that x minus 1 is a factor of this cubic polynomial, and that means so it means that yes, of course, because by virtue of the factor theorem, that f of 1 gives us 0, and so x minus 1 is a factor of the root of this equation. Now, having found that x minus 1 is a factor, it means that 1 is a root, right? Now, where do we go from here? So the next step now is having found one of the factors, you now break this down into a quadratic equation. And how do you do that? You do your original equation divided by new factor you just found. And when you divide that, you're going to get a quadratic equation, which you can now solve to get the remaining 2 roots using any of the other outline methods that we looked at during last week's class, right? So that this is pretty much the hard part, finding a partition. And of course, this was easy. So we just tried to, we just tested 2 numbers and we were able to find one of the factors. It might not always be that seamless and easy, but then when you do find that factor, the next thing for you to do now is to break this equation down. So you divide this into a, you divide this equation by this, and whatever you get as your quotient to answer will be a quadratic equation. And then you now solve that to find the 2 other roots, which in addition to this third root will be the roots of your cubic polynomial. Now I say this with the assumption that we know how to divide polynomials. I mean, I don't know if you don't know how to do that, just if anybody's in the class, we just signify. But I think that should be common knowledge on how you're going to. So it's just like I said, it's just like long division. So if, for example, they tell you to do 2000 divided by 6, you draw that line, and then you now put 2000 for 6, and then you start dividing, right? Like your normal long division method. So the same thing applies for polynomials. So you have x cubed minus 2x squared minus x plus 2, and then divided by x minus 1, and then you now start your division. So x cubed divided by x is x squared. Then you now do x squared times x, right? You answer x cubed on that here. X squared minus times minus 1 minus x squared, right? Minus x squared on that here. Then you now do the line, subtract, then you now bring down the next one. So it's like I said, your normal long division process. If you are able to do that successfully, your answer here above is going to be for that equation. It's probably going to be x squared something. When you arrive at that answer, then you now solve that for that equation. Then you have the methods that we have explained, and you are going to get 2 roots, right? And then in addition to these roots, you're going to have 3 roots. And we're having 3 roots because this is a cubic polynomial. So as expected, you're going to have 3 possible solutions to that equation. So having shown you how this works, I will probably leave this as an assignment or something for you to tell, and if you have any issues, you can also bring it back to me and find the other 2 roots of this equation. I've been able to find one, which is x minus 1. So now what's left? I mean, like I've explained what's left is this equation, find that equation, and get that 2 roots of this equation. So this is an assignment, and I hope those of you who are on this video, on this call, will have time to be able to do that. So moving on to the next slide now, we're going to go into logarithms and their kinds properties. So what does a logarithm actually mean? So logarithms and indices are closely related, right? So I think I would assume that you have some knowledge of what indices. So we're talking about power, reach the power of. So that's what we mean when we talk about indices. So there's a very close relationship between logarithms and indices. So the basic definition of a logarithm is as written here. So if a raised to the power x is equal to b, then log b base a is equal to x. Now, if you notice, a is written here very, very small as like a subscript. So why is that case? That is, it's not like it's multiplying b, no, it's simply signifying the base of the logarithm. So if you remember another base, yeah, several bases that can exist in base 2, base 3, base 4, base 5. What these bases actually represent are the modules, the quantity in which perform the operation. So of course, we are in base 2, we're going to count in 2, right? We're in base 7, we're counting 7, we're in base 16, you're counting 16 or base 8, whatever it is. So of course, the logarithm will also have bases, right? And that's taken from, so if you notice from the index, the rearrangement, right? So a to power x equals to b, the power x now becomes the result, and then you do log of the answer is your your base, right? So in this, we have the base and power. And so that base literally becomes base in logarithm. So this is definitely the basic definition of how logarithms come to be. And so we have, of course, laws that guide the operations of logarithms. And we've applied 3 key ones here, important ones. So if you have log of, so of course, all of these are going to be base of A to avoid substitution. So you have log of 2 numbers multiplying each other, so log x, y, or x times y. The law of logarithm says that you can separate that into log x base A plus log y base A. So notice how both of them still carry the same basis, but now we separate them into x and y and then put an addition sign in between. So now the same thing applies. This is much like when you were learning with so as I was saying, so the log for multiplication, when you separate it, it becomes addition, right? And then the x and the y take their different logarithms and same base. Now for division, it's the same thing, but now subtraction that separates it. So x takes its own base and y takes its own base, but now it's separated by the subtraction a minus m. So of course this works vice versa. So you can also go from here from log a base x plus log a base. And the only criteria, the only thing you have to make sure is that they have the same base, right? That's the only way they can be combined back to this. If the bases are not the same, then this law does not work. It's important to know that if the bases are not the same, then this law does not work. And the third law is log x raised by n of base a. So the law of logarithm says that n can come down. Of course, n is the power of x in this first instance. So the law of logarithm says that n can come down and multiply log x base a, right? Can come down and multiply log x base a. Wonderful. So there's also another logarithm known as the change of base. Change of base. Now, what does that mean? So in the case where we have log x base b, right? Log x base b. Now, one thing to note in logarithm is some bases are easier to handle than others, and sometimes it will be more convenient for you to do operation in a particular base than the one you are given to work with, right? And so there is something called change of base, which enables you to manipulate from one logarithm base to another logarithm base. And now this will state that if you are given log x base b, so this is supposed to be a subscript, this b is subscript. If you are given log x base b, you can apply a change of base. So let's say you are given base 2, right? And you want to change base 10 because base 10 is easier for you to work. And so you have log something base 2, right? You want to change base 10. And change of base, you can actually do this. And then it will be presented as log x base a over log b base a. Now that 10 is the a in this case that you are changing to. However, you are now going to have 2 an dual equation in division in your change of base. So the x and the b take their own logarithms, and then the new base now comes in, and then it's dividing. So log x base a over log a log b base a. So that's how the concept of change of works. Change of base works. Now, another thing for us to note is the natural log. So there's something called the natural log, which is denoted by ln x. So it's basically the log of a number, the base as e. Now, e in maths is a special number which is represented by 2.718. So for example, if you have log a base e, right, it's the same thing as saying ln a, right? Ln a. So anything that has the base as that e can be changed to simply be ln whatever it is, right? And so it's referred to as the natural logarithm. If you check your 4-figure table, you'll also see tables that have these things there. So it's important to know what these rules are. When to apply them, when can you convert from this, when can you use this, when can you not use this, right? And those will be key in being able to solve logarithm questions when they arise, right? So we have some examples here that apply the logarithm properties. So we'll just go through the examples. So now the first one is the product rule, right? So remember what I said about the product rule. If you have 2 numbers multiplying each other, they can be separated to have a plus sign in between, and then they have the same base. So here, you notice our base here is 3, right? So it will now be log 9 base 3 plus log 7 base 3. And the same applies to quotient when you have a division. So you now separate both of them, and of course the base is 7. So it is 2, you separate both of them, and then you put the subtraction sign in between. The next rule is the power rule. So we have log 25 raised by 3 base 3. So you, by virtue of the power rule, remember what I said, that the power is up here and now comes down to multiply the ruler. So in this power, the 3 is going to come down here, multiply log 25 base 3. And when you subtract whatever log 25 base 3, then you finalize your answer. Change of bar, of course, change of bar of base, sorry. So you have log 4, log 64 base 4, which is actually very easy something to handle because 4 is like a power of and an power of 4, right? But let's say for some reason you want to change the base, right? So it's going to be log 64, and I'm going to be 10, right? So log 64 base 10 over log 4, which is our previous base here, so it now comes up and then takes the base of 10, right? So log 64 base 10 over log 4 base 10. Right, so that is what entails. So now you might be asking the question: we have log 9 base 3 here, log 7 base 3. How do you now get 2 and 3? How do you resolve that without having to use the calculator? Of course, you know that calculator something, but then it's very simple, right? So remember what I said from the beginning: indices and logarithms are actually related, right? So if you were to looking at that general form, what are indices and what are indexes and logarithms? Log 9 base 3 is simply you saying 3 raised to the power something, give me 9. Whatever that something is the answer to my log 9 base 3. Right, so it's good for you to be able to master that relationship. A is by x equals to b. Now, when I do log of b base a, that power now is now my result, right? So I'm more like working backwards here now. Since I already have the logarithm and I want to find the answer is index to that indice that's represented when you convert it. So I don't know if you're following, right? But that's exactly what it is. So without having a 4-figure table or a calculator, I can simply, because I know that 3 is over 2 gives me 9, I can simply just write that log 9 base 3 is 2, right? Now, this is pretty straightforward because the base and the number you're going to logarithm of are factors, are squares or multiples. That's right, or multiples of each other. And so hopefully that is the case more often than not. But in the case where you got a multiple, then you now have to use calculator because now you're going to be using decimal point and fractions and all of that. So the same thing applies here. Log 27 base 3. I asked what 3 raised to the power 1. Now this 3 I'm going to ask is base. 3 raised to the power what? 27. And that's 3, right? So 2 plus 3 is 5. Same thing applies here. 2 raised to the power what? 3.8. 3 raised to the power what? 3.8. That's what these people are showing us that it's the way to resolve this person calculator. So like I said, it applies when you have multiples, right? But in the case there are no multiples, then yeah, you have to resolve the calculator. So That's how this is resolved. And then, of course, using the logarithmic properties. So, for example, here, 10 raised to power, there's no whole number that you raise 10 to 11 to 64, right? So, obviously, this was not the calculator because you can't figure out that 10 raised to power 1.8 to 64. There are cases like that, but then more often than not, you just take simple cases where a few seconds of thinking, you can just find the index, and that's the value of that algorithm. Exactly, so that's how it works. So, we are going to go. We are going to go into linear inequalities next, right? So normally we are used to equations where we have something on the left hand side, we have something on the right hand side, and what separates those two equations is an equals to sign. An equals to sign. Now, have you ever thought that something else would separate those two equations, something that is not an equal to sign? And that's where inequality is coming. Because in linear equality, we are expressing ranges of values and not just a particular value. So, of course, if I say what are the numbers that are equal to, there is only one particular answer for that my question. There's only one number that's equal to 2, and that number is 3, right? However, if I now say give me numbers greater than 2, of course, there is an infinity of numbers greater than 2. Right, so as I was saying, we have inequalities. So instead of an equal to sign, you have a greater than sign or a less than sign. So if I said, give me all the numbers that are greater than 2, I will not just list one number, I will list a plethora of numbers, I will list multiple numbers. So numbers greater than 2, I have 3, 4, 5, 6, 7. So it's why it's called that highlighted in the definition that there are a range of values, it's not just one value. So that's how inequalities are. Now, on the number line, because of course you have to graphically represent some number line. On the number line, if it was an equal to sign, your number line will just be to point out what particular number on the number line is the answer to this equation, is the result, right? But however, on the number line, you have a range, you have a point, and then you have a range. You have a boundary, but you have a range. It's not just one figure, it's not just one value. And so, for example, if your inequality was x less than 2, it would mean that your inequality is asking for all the values of x less than 2. And so you just come to x, you just come to 2 on your number line, draw a circle that you have over here, and then now, since it's less than, you're going to go in one direction. So all numbers less than 2, right? So you now draw an arrow from 2. It's not highlighted here for some reason, but then you now draw an arrow from here, just pointing in the general direction of numbers that are less than 2. And that's how you have represented that inequality graphically, right? And so just point, just draw a line, an arrow that points in this direction. And you're going in this direction, because this is the direction where numbers that are less than 2 on the number line are situated, right? If it was x greater than 2, you would still do the same thing, but then you now point your arrowhead in the direction of the numbers that are greater than 2. And so that's how you present it. Now, another important nuance and something to note is when you have greater than and greater than or equal to, right? So, for example, you have x is greater than or equal to 2. Now, there's a difference between that and representing x greater than 2 because you have greater than or equal to. And so, what will now make a difference on the number lines? For the case where there was no equal to, you just draw an open circle, right? And then point your arrowhead in direction depending on what the equality is asking. However, when you have greater than or equal to or less than or equal to, you will do the same thing, but the only difference now is you're going to shade the inside of your circle. You're going to shade it to show that that's your particular point is inclusive of your range. So if I were to ask you for x, the number of x greater than 2, you're not going to include 2 because 2 is not greater than 2 is equal to. So you just start from 3, 4, 5, 6, 7, 8, 9, all until you add infinity. However, if I were to say x is greater than or equal to 2, it means that I would shade that 2. So if anybody sees it, you know that okay, this on the boundary is also part of the value that the person that owns the is asking for. And so, like written here, open circle show less than, closed circle show less than or greater than number lines. And of course, vice versa, this is simple. This is simple for whatever inequality you come across. As far as I able to simplify and represent the number line, we're good to go. So of course, we have an example on number line, just reiterating everything I said in the previous slide. So an open circle shows that it doesn't include the value. Closed circle shows that it includes the value. So for example, show x less than 3 on number line. And open circle needs to be indicated that 3 on number line shows that social inequality doesn't include number line. So in this example, we have x less than 3. And so our arrowhead is pointing in one direction, the direction of the numbers that are less than 3, right? And then if you notice, the head of the circle is not shaded. Now, it should tell you that there is no less than equal to, everything is left open because it's just less than. And so it means that this thing, if someone sees graph now, the person will instinctively understand that 3 is not included in this range because the circle is open. However, it was included, then you use color it, whatever it is you want, colors, just shade it, right? So that's how you indicate. Now, for quadratic inequalities, we're also going to be looking at up next how we solve quadratic inequality, right? So the first thing to do is bring all the terms to one side, right? So you're going to be having just like the quadratic equality. So now the only difference in the quadratic equation and this equation is that the inequality sign has come in, the equals to have been thrown away. So now you're doing inequalities. So basically, you're going to be solving them like waves of that equation, right? You have to find the pick point. The pick point are what the roots of the quadratic equation. So when you're doing quadratic equation, you find the root and those big points here that your call quadratic equation called and dissect the x axis. So that's why it's called critical point, right? So he will apply that same method. And so you imagine that inequality is gone and you place an equal sign and you solve it normally. However, there's a difference in the final answer. So when you find those your roots of critical points, it's not equal to anymore. However, it's an inequality. So you have to know whether you need to represent greater than sign, greater than equals, less than sign, less than equals, and that's why we now have a sign diagram, right? So I'll explain that when we solve an example, explain what that is. So let's quickly get right. So an example of a solved quadratic inequality. All right, so here we have minus x squared plus 6x plus 7 is greater than or equal to 0. Now we can clearly see that this is an inequality because there is no equal to sign, and we have a greater than or equal to as the replacement for equal to sign. So first of all, we take all the terms to one side. Of course, all the terms are already arranged on one side, right? So the next thing to now do is determine the critical numbers or the roots, like I have said. And of course, if you replace the greater than sign and false for the time being, this just resembles a normal quadratic equation that I believe we should all know how to solve by now. So when you do that, you just follow any of the normal methods you know and find the roots of the equation, right? So that's the process that happened here. I'm not going into that detail because I assume that we all know how that works, right? So when you now find the roots, so like in this equation now, we found the roots to be x plus 1 equal to 0 or x minus 7 equal to 0. And so our x, or the root of this equation, this quadratic equation, is minus 1, x equals to minus 1, or x equals to 7, right? So these are the critical numbers. Now these are going to also be the roots of our quadratic inequality. But now there is a slight distinction between this and the quadratic equation. Because in the quadratic equation, you simply just say x equals to minus 1, x equals to 7, and voila, that would be your answer, right? Or not quite the case with inequality, because now we have a range. So you have to decide for yourself, is it going to be greater than minus 1 or less than minus 1, or where is the range line? We know that the boundary, so that's where the boundary is going to be minus 1. But are we going to go to the left or going to go to the right? And so we have something called a sign test. So it helps you just draw a number line so you visualize it. So you take your two critical points, minus 1 and 7. Now, as you can see, they are shaded here because in our quadratic inequality, we have an equal to accompanying greater than. So it means that these 2 points are included in the range because you have equal to, and so you shade them, right? So now, how do you determine the sign? We do a sign test. So minus 1 is our boundary, minus 7 is our boundary. And by drawing this on the number line, you see that you divide this number line into 3 different portions. You have this one over here, this one in the middle here, this one here. So now what do? You take a number from each of the 3 different portions and test it in your quadratic equation, right? Now, what are you testing for? You are testing for the sign of your final answer. So let's just follow this sequentially so that it's clear what's going on, right? So from this outer portion on the number line, so of course, this other portion now is from minus 1 down, right? Then this other portion is between minus 1 and 7, and here is from 7 up, right? So here we choose minus 3, right? And now we do f of minus 3. We know what that means, right? So far, for that equation, anyway, we see x replaced with minus 3. And now solving that and calculating that. So whatever our answer is not relevant actually. The major thing or the priority here is to determine what the sign is of the final answer. Now, if you resolve f of minus 3, your final sign is negative. So you hold that to keep it. Now you pick another number within this middle portion. So here we pick 0. Now f of 0, if you have to resolve this, of course, is going to be positive because this x goes to the x goes to the left, 7 is positive, right? Now the third portion is here from 7 upwards, and now we pick a number and also test for the sign. And if you do that, you see that you're going to have a negative, right? So having known that, this now represented on the sign chart, right? So we know that this portion gives negative. Now we know that because this is below this boundary, right? This critical point. So these critical points are like inflection, they are the boundary. So we know that by simply testing one of them in this area, it means that that's the behavior of everything below this critical point in this area. By testing one value in this area, we know that that's the behavior of all the other values in this area. By testing one value, we know that behavior of everything. So we can generalize and say this portion is giving negative answers, this portion is giving positive answers, this portion is giving negative answers. Now, how does that help us, right? Our initial equation is saying that we want to determine the range of values for which minus s squared plus s plus 7 greater than or equal to 0. Now, when something is greater than or equal to 0, what does that mean? It means that it's positive, right? Because all the numbers greater than or equal to 0 are positive numbers. 0, 1, 2, 3, 4, 5, 6, 7, and so forth. Now, according to our sign test, here in this portion of this number line, we have positive numbers. We see that it's only in the middle, right? So we tested this area and we got negative as our answer. We tested this area and we got negative as our answer. So in this middle area that we have positive as our answer. So it means that the range of values that we need is in this middle area, right? Because it has to be where we have positive. So our quadratic equation, our quadratic inequality for it to be satisfied says that you have to be greater than or equal to 0, which is positive, right? So now that we have found our range, you know that x, where x is between minus 1 and 7, is what satisfies that equation, right? And so our final answer would be minus 1 greater than x. Yes, no. So how you would write that? Let me quickly just illustrate that so that we see what that actually means. So it will mean that having found that this is the area where our answer lies. So we represent that as minus 1 less than x less than 7, right? So this is the answer to your inequality, right? Or you can write it as x is greater than minus 1 and x is less than 7. So these two answers are the same. Now this one is the simpler way of writing, right? Because from here now you see that any answer so greater than or equal to, so note that. So it's not just greater than, so I represent that with a dash, less than equal to, or less than equal to. Now it's not just so why that's the case is because within this range of values where we know that this is where our answers lie, anything that is here is greater than minus 1, right? So we say that x is greater than or equal to minus 1, and anything that here is less than or equal to minus 7. Now this answer, right, can be combined to give us this answer, right? So this is like a shortened form. So this is saying minus 1 is less than x. So it means that x is greater than minus 1, which lies in this range. And also saying that x is less than 7, which lies in this range. This is like a shorter representation of what the answer to that inequality is. So this is fine. This is also fine, right? But also, I mean, it's better to represent it as a conventional form. Now, if we had this equation and the equation had told us from the beginning that we want minus s squared plus 7% to be less than or equal to 0, it means that our answer will be different now. Even though we have the same critical point, our answer will now be where the negative values lie, right? So here and here. And that would be x is less than or equal to minus 1. And x is greater than or equal to 7, right? Because these are the points where x we have negative value. So assuming that our equation was less than or equal to 0, it means that we want negative numbers. And so the negative numbers from our critical points lie where x is less than minus 1, so going down minus 1, minus 1, minus 1, minus 1, and so on. And the negative numbers also lie again here where x is greater than 7, 8, 9, 10. Now you see that this cannot be combined because it's not within the same. So like, so the first one was here, right? They share the common space, but this one is on this side, and this one is on this side. So your answer will have to be left like this. There's no way you can combine it into something like this, right? But then that's simply the way linear inequality works. So there is the only major distinction now is this sign test. You have to figure out where does where's the range, where does it lie, and you know you can do it by doing this sign test. Of course, you can do it also by doing the graph, but then that should be on the scope. I mean, before you finish plotting the graph and everything. So sign test is what helps us to determine, okay, am I going to have a less than sign or an equal to sign for my physical points? And then with that, you're able to now actually get an answer to your inequality. So the next one we're looking at now is absolute value inequalities, right? So what do we mean by absolute value? So this symbol here now that is surrounding this x means that it's the absolute value of x, right? So the absolute value x less than a means minus a, less than x less than a. Absolute value of x greater than a means x greater than x less than minus a or x greater than a, right? So some examples, for example, we have here that our absolute value of 6 minus 1 is less than 3. And so we now represent it in more conventional form. We're using the absolute value that minus 3, which is minus 8, is less than x, less than 3. So this is what you do when you have absolute value inequalities. So, but for the example here, so I think this is something we're familiar with what I explained in the previous example here. Here, there's a combination of those two answers. But here we have this or this. So it's left like this because simply cannot be combined into something as succinct as this. But then this is still the answer, regardless. So then, more examples here, of course, on absolute value inequalities and how they can be resolved. So, take your time. I think this slide is given out. Take your time and look through them and then familiarize yourself with them. Right. So, with that, we come to the end of our slide for today. I think yes. So, just a brief summary. We looked at polynomials and the factor theorem and that theorem that apply to them. We looked at logarithms, we applied rules of logarithms and different laws, and also included change of gradient to simplify the expressions. And we looked at inequalities, linear, quadratic, and absolute value inequalities. And so I hope that most of the concepts that I explained we have prepared. If you're having any issues, now's the time to ask your questions, and then we'll attend to them as the case may be. So question and answers from anybody on the call, so that we go over concepts that have not been made quite clear, and then see and hopefully what has topic and concepts are made more clear when you solve problems on your own. So it's important to solve problems each and every day. So any questions? Any question? I think I have only one person. This for EK Koronya Chipike. Can you hear me? Hello, can you hear me? Okay, I don't think you can. But anyway, so since there are no questions, so I believe that the concept of today's class and explain as thoroughly as possible. If there are any issues or complaints or questions you have, you can also be able to ask them ask follow-up questions in the next class. But I believe that we've done quite a very thorough job of explaining on the concept of all inequalities, logarithms, and opinions. So in the absence of any question, we come to the end of today's week 4 class for the math JUPEB tutorial, where we got polynomials, inequalities, and logarithms. So it's a wonderful spend over an hour here for breaking down the subject for you. Thank you for the time, the opportunity to be able to do this. I think, of course, as usual, the calls are always being recorded. So if anyone was absent, feel free to watch the videos, solve the examples that we're given, and then get back to me if you have any issues. So yeah, thank you very much for your time. It's a wonderful class, wonderful evening, and then hopefully we'll see you all again next week. Muchas gracias. Good night.